All right, let's get right into it. Today, we're diving into this incredible microscopic battle that, believe it or not, shapes our entire world. It's all about a constant atomic tug of war for one of the most important particles out there, the electron. So, let me ask you a kind of weird question to get us started. Do atoms have personalities? I mean, do these tiny little building blocks of everything actually have their own unique traits, their own desires and tendencies?
And the answer? Oh, you bet they do. When it comes to electrons, atoms have very distinct personalities. And if you can understand those personalities, you basically have the key to unlocking the secrets of all chemical bonding.
So, let's meet our first atomic personality trait. We can think of this one as desire. It's all about how badly a single, lonely atom wants to snatch up a brand new electron for itself. The proper scientific name for this is electron affinity.
Now, here's the textbook definition. It's the energy that gets released when a neutral atom grabs an electron. You can almost think of it like a sigh of relief or a burst of happiness from the atom. The bigger that release of energy, the more that atom really desired that electron.
So yeah, the easiest way to think about it is this. High electron affinity just means a strong, powerful desire to get a new electron. And notice I said get. This isn't about sharing. This is about pure, outright acquisition.
But, this desire isn't just random. Just like a lot of things in chemistry, it follows a really predictable pattern, a trend across the periodic table. So let's take a look at who wants one the most. And here's the cheat sheet. As you move from left to right across the table, the nucleus of the atom gets more and more positive. That means its pull gets stronger, so its desire for an electron goes up. But as you go down a group, the atoms just get bigger. Their outer shells are so far away from that nucleus that the pull gets weaker, and so does their desire.
Of course, you've always got a few exceptions, right? Just think of atoms like the noble gases as being perfectly happy and content just the way they are. Their electron shells are already full and stable. They have basically zero desire to mess up that perfect situation by grabbing another electron. You could say they're the introverts of the atomic world.
Okay, so that's how an atom feels about getting a new electron when it's all by itself. But what happens when atoms aren't alone anymore? What happens when they bond together and they have to share electrons? Well, that's when we get to the main event, the great electron tug-of-war.
And the force that drives this whole tug-of-war is called electronegativity. Now, the key word here, the one you've got to remember, is shared. This is not about getting a new electron from somewhere else. It's all about how hard an atom can pull on electrons it's already sharing with a partner atom in a bond. Honestly, this is the perfect way to picture it. Just imagine two atoms, and they're both holding onto the rope, the shared electrons. The atom with the higher electronegativity, that's the stronger competitor in the game. It yanks that rope, pulling the shared electrons closer to its side.
And hey, this should look pretty familiar. Just like electron affinity, electronegativity follows the same basic trends for the exact same reasons. As you move across the periodic table, atoms get smaller but have a stronger nucleus, which makes them way better at this tug-of-war. And as you move down, they get bigger and weaker, and their pull fades.
And standing at the very top of the podium, we have our champion, fluorine. It gets a perfect score of 4.0 on the Pauling scale, making it the most electronegative element, period. Absolutely no other atom can pull on shared electrons with more force than fluorine. It's the undisputed champ.
So what's the point of this whole atomic tug-of-war? Why does it matter who wins? Well, the outcome actually determines the entire nature of the chemical bond itself. How those electrons end up being shared, or, not shared, is literally everything.
So how do we keep score in this tug-of-war? We use something called the Pauling scale. Think of it as the official rulebook. It gives every element a score for its pulling power. And by just comparing the scores of two atoms in a bond, we can predict exactly what kind of relationship they're going to have.
And the process couldn't be simpler. It's really just 3 easy steps. You find the electronegativity value for each atom, you subtract one from the other to find the difference, and that one little number tells you the entire story of how they're going to interact.
So if the difference is 0, it's a perfect tie. The electrons are shared totally equally. We call that a non-polar covalent bond. If there's a small difference, one atom tugs a little bit harder, which creates a polar covalent bond. But a big difference? Whoa, that's not a tug of war anymore. The stronger atom just rips the electron away completely, and that forms an ionic bond.
Okay, let's wrap this all up and put these two concepts head-to-head in a final showdown. They sound really similar, I know, but they are describing two very, very different atomic personality traits.
Here is the whole thing in a nutshell. On the left, electron affinity is all about a single isolated atom's desire to gain a totally new electron, and we measure it in actual units of energy. On the right, electronegativity is about an atom's power to pull on electrons it's already sharing in a bond, and it's just measured on a relative scale. So one is about gaining, the other is about sharing. That's it. That's the fundamental difference you need to remember.
So why does any of this matter? Because these personalities, this desire to gain and this power to pull, they aren't just random facts for a chemistry test. They are the fundamental rules that decide which atoms will bond together, how they'll do it, and ultimately, they determine how molecules, materials, and even life itself is built from the ground up.
So, I'll leave you with this final thought to chew on. If everything we see, all matter, is just the result of a constant tug-of-war for electrons, then what exactly is a chemical bond? Is it a partnership, a fierce competition, or maybe it's just the beautiful, stable result of a fight that's finally reached a perfect balance?